Now that we've seen what graphs are, let's talk about some algorithms we can run on graphs, and then also let's talk about how we could implement graphs. So the first algorithm we're going to see is a breadth-first traversal. You can think of a breadth-first traversal as similar to a level order traversal of a tree. And the idea with a breadth-first traversal is we're going to start at some node. And with the graph, what's nice is you can start anywhere. We'll start at A because it's the first letter, but there's no reason that we couldn't start at D or F or any other node. So we start with A, then we look at its neighbors, then we look at its neighbors' neighbors, and by doing that, now we've seen every node in the graph. Now again, we don't need to start with A. We could start with E, and then its neighbors are B and D, and then B and D's neighbors are A and F, or I should say the new neighbors, the ones that we haven't visited. Then the new neighbors of A and F are just C. So that gives us our breadth first traversal. So let's go and do this a little more specifically, seeing the steps we would take. So to do a breadth first traversal, first you would pick your starting node, and if you were implementing this, you would add it to a queue, and then you would add the neighbors to the queue. So here we add B, and then we've added C. Then we would take the first neighbor of A, which is B, and we would look at its neighbors. So we have D, E, and F are neighbors of B. And then the neighbors of C, well, we've already visited F and A. The neighbors of D, we've already visited F and E. The neighbors of D, we've already visited E. So there's no more nodes to visit. And then my breadth first traversal is A, B, C, D, E, F. And again, the order of this, it just depends on which node we start at. For a depth first traversal, think of that as similar to a pre-order traversal where we visit a node and then we're going to visit one of its neighbors and one of the neighbor's neighbors and so forth. And then when we run out of nodes to look at, we'll backtrack. So here we start with A, then we visit B, then we visit one of B's neighbors. And again, we'll choose the neighbors in alphabetical order. So we'll choose D. Then D's neighbor will visit E. Now E's neighbors are B and D. We've already visited those, so we need to backtrack. And D has another neighbor we haven't visited yet, F. And F has a neighbor we haven't visited yet, C. So there's our depth first traversal. Again, we visit A first, then B, then D, then E. Notice we're just going deeper and deeper into the graph as far away from the root as we can. E doesn't have any new neighbors, so we'll backtrack, and D has a new neighbor, F. And then from F, we'll visit C. And from there, there's no nodes with neighbors that we haven't visited. And again, we can implement this using a stack where we add the neighbors to the stack. Something with LIFO order works here very well. We've already seen how to work with trees. Sometimes converting a graph to a tree makes it easier to work with. And one of the ways we can do that is with what's called a spanning tree. So a spanning tree is the same as the original graph. It has all the same nodes, and we remove edges until the graph becomes a tree. And so here you can see we removed some edges and we're left with a tree. Now, we could also remove these three edges, giving us this spanning tree, or we could remove these three edges, giving us this spanning tree. What's the best way? It just depends. Now, there is something called a minimum spanning tree where we try to reduce the total cost of the edges or the weights of the edges, and there's an algorithm that'll do that as well. So the idea there is that you put all of the edges onto a heap that's ordered by the weights, and you take the smallest weight edge off, see if it adds a new neighbor. If it does, you add that edge to the spanning tree. Otherwise, you ignore it, and you keep doing that until you wind up with a connected tree. So if we're going to implement these algorithms, we need to have some way to represent a graph in our program, and we'll talk about two approaches. So the first approach is an adjacency list. We're going to keep track of all the vertices, and each vertex will have a linked list to all of its neighbors. So there's an edge from A to B, so we'll add B to A's adjacency list. A also has an edge to C, so we'll add C to the adjacency list for A. B has 4 neighbors, A, D, E, and F, so we'll add those edges to B's adjacency list. Don't get too hung up in this data structure. This is an array or a list or something. And then each of these nodes in whatever data structure this is has access to a linked list of nodes. Don't overcomplicate this in your thinking. This is something that you could implement with what we've seen so far in this class. So now let's take a look at C. C has neighbors A and F. D has neighbors B, E, and F. Again, you'll notice all we're doing is creating a linked list of the nodes that are neighbors to the node that we're focused on. So E has neighbors B and D, and F has neighbors B, C, and D. So this is our final adjacency list of this graph. Another way we can represent graphs when we're implementing them is with what's called an adjacency matrix. So the adjacency matrix is going to have a row and a column, one row, one column for each node. So you can see here's the A column, here's the A row. And we're going to put a flag at the intersection of any two nodes that share an edge. So for example, there's an edge from A to B. So we'll put a 1 in row A, column B, and in row B, column A. For the edge AC, we put a 1 in row A, column C, and row C, column A. So for edge BD, we add a flag row B, column D, and row D, column B. For edge BE, row E, column B, row B, column E, and so on and so forth as we go through the edges of the graph. Now, one thing you should notice is that this matrix is symmetric, and that's because this is an undirected graph, and we'll see a directed graph in a moment. So this is our final adjacency matrix for this graph. Now, if we have a directed graph, then our adjacency lists will keep track of the neighbors of each vertex. But notice now there's an edge from A to C, and C is in the adjacency matrix for A, but there's not an edge from C to A, so A doesn't exist in the adjacency list of vertex C. We could also implement this with an adjacency matrix, and here the starting node of the edge is the row, and the column is the ending node of the edge. So here you can see A has edges to B, C, and D, and all the other nodes only have one outgoing edge. And now you'll notice that this matrix is not symmetrical. If we have a weighted graph, then we can add weights in the adjacency list, or if we want to use an adjacency matrix, then we can put the weights in the adjacency matrix. And keep in mind, this isn't just limited to numbers. If we wanted to keep some sort of object to represent that edge, we could do so as well. So that's a quick overview of some graph algorithms and some strategies for implementing graphs. For CSE 205, this isn't a major topic. In fact, you'll notice we haven't looked at any code, but graphs are a very important topic for computer science in general. There's a lot of problems that they will help you solve, so it's good to get some exposure to them.